All right, so let's take a look at a problem from the text and show how that problem can be coded and solved using CVX. This is a problem from Chapter 4. It's the design of a cantilever beam, and the code that I'm going to show you is included in the CVX distribution that you should have downloaded already. So you've got this code. It's in the example files. I'll show you exactly where when we get to it. And so the purpose of this video is to describe the problem very quickly, which I think you'll get the problem quickly, and then show how it's coded in CVX to give you an example of something a little more complicated than what we did in the introductory video. So here we've got this cantilever beam problem, classic optimization problem. The beam is rectangular cross-section, and it's got some number of segments where each segment has a specific cross-sectional area parameterized by the width and the height. And then we're going to load the beam at the end, and that will, of course, cause the beam to deflect, and there will be stresses in each of the segments of the beam that are a function of that loading. So here's an example picture of a 4-segment beam where the cross-sectional areas are getting smaller and smaller as we move away from the fixed point on the left side here. We have the force applied over here on the right-hand side. Okay, so what's the design here? Well, the widths and heights of the segments are the variables that basically parameterize this entire design. So one issue that we have is the total volume of the beam, or that could be looked at as weight, right? So segment 1 width times height plus segment 2 width times height, etc., for all n segments. This gives us total volume. If you add in some material properties there, you get to weight. We want to bound the width and height of the segments, so these will be constraints. We need to define the min-max width, the min-max height for each of the segments, and then the aspect ratios are bounded as well. So the height divided by the width must fall in some min and max value. And then we have this expression, which gives us the stress in each segment. So here F is the applied force. 6IF divided by the width times the height squared must be less than or equal to the maximum stress for that particular segment. So each segment has some maximum stress that it can withstand, and we want to make sure that that's not going to get exceeded in each of the segments. We also want to constrain the amount of deflection that we will get on the end of the beam. So that is this constraint here in Y. And in order to find the deflection, we use this formula here. This is the deflection in the this is the deflection in the ith end of the beam, where F is the applied force, E is the Young's modulus, VI is described here in this function. And so these just tell us how the beam is deflecting. And this is going to be set up as a geometric program. This is an expression of the optimization problem. Okay, so we want to minimize the sum of the width times the height. So this is minimizing volume or weight. And then we have our constraint on the width, our constraint on the height, our constraint on the aspect ratio, our constraint on the stress in each segment, and our constraint on the deflection of the beam. Okay, so over here in Matlab, here we have our We are in the CVX, CVX directory that we installed from the last video. And if I come down here to examples, this example happens to be, so just so I show you the whole navigation here, if we go to examples, CVX book, and then let me just close all these so it looks like it will when you guys open it. Here, chapter 4 through 11 problems. This problem, as I mentioned, is in chapter 4, and it is the cantilever beam problem. So let's go ahead and open that up and take a look at this problem. So here in the comments, it talks about, the code. Here is the geometric program that is from the text. So we're minimizing the sum of the widths times the heights, subject to, once again, our width constraint, our height constraint, the aspect ratio constraint, our constraint on the stresses, our deflection constraint. And then if you look at this section here, this is the recursion that you saw when we were looking at the text for dealing with the deflection. All right, so here these constraints here are dealing with the deflection, y sub I, and then this is a constraint on y1. So here's a description of the variables, and we move into the actual code. Okay, so in this example, n is equal to 8. So we have an 8-segment beam. And now these are constants that the author of the code created. These are not actually given in the text, but we need to define what is the minimum acceptable width, maximum acceptable width, height, aspect ratio, stress, deflection, etc. And then a unit force and a Young's modulus of 1 for this problem. Again, not given in the text, just made up values for the purpose of solving this problem. So all these are simply constants. All those constants are defined, and they're going to be used inside the optimization. Okay, so then we get our CVX begin mode, and you'll notice this GP. GP stands for geometric program. Talk a little bit more about that later, but let's move through the code. You'll recall from the last video, any variable that we use in a constraint or in an objective function inside of the CVX code block needs to be declared, and so here we're declaring those variables, right? So the width constraints, the height constraints, v and y, these are all variables that will be used. And now we move into our the statement of our objective problem, our objective function, which is this minimization, minimize w prime times h. So this is just if w is a vector of widths and h is a vector of heights, we take their dot product, and that gives us the volume. We take the dot product gives us the total volume, right? So that is our objective function. Now our constraints. So in this line here, we are setting up this variable d to be 6 times the force. This is ones, gives us a vector of ones that is n long. It gives us a matrix of ones, which is n by 1. So in this case, it's going to be a vector of ones. And we're doing a element by element division of the Young's modulus times a vector of 1s times the width times the height cubed. So if I just bring this back over here, you'll see where these terms are coming from. Okay, this is going to be part of this recursion. And now here's the recursion itself. So we're using this expression D inside the recursion, and this is the recursion inside this loop. So we're looping from 1 to n for each of the segments. Down here, we have our constraints: constraint on width, constraint on height, constraint on aspect ratio. This is the constraint on the stress inside each segment, and this is the deflection constraint, right? And notice that the deflection constraint, where this gives us the deflection at the end of the beam, right, y1, but it's a function of all the other deflections which are taken care of recursively. And then that ends the statement of the optimization function. It's obviously called, it's solved, and then now this is just a displaying of the output. So the optimal widths and heights, and then the W and the H vectors are printed out. This is the minimum volume of the beam, is simply the sum of the dot product of the widths and the heights, and then there's a plot of the actual beam itself. So that's the entire program. Let's give it a run and see what happens. So this takes a little bit longer to run than the last one we saw. And so here we are with our outputs. These are the widths per segment. These are the heights per segment. You can see we're getting tight on some of the constraints at the end here. The optimal volume that we have here is 42.3. And here is a graphic 3D depiction of what the beam would look like. Okay, so good example here, something a little bit more sophisticated. I want to come back to the code, and here this talk a little bit about this GP mode. So GP here stands for geometric programming, and so what is we talked in the last video about DCP and what is and is not permitted in DCP. So when we call GP mode, it allows a geometric program, which is a specific type of optimization problem, to be specified in a way that may violate DCP. It's still convex. You'll recall we talked about DCP, that the conditions under DCP are sufficient but not necessary for convexity, so we can have violations of DCP that are still convex. So what's happening here is that when we call GP, if you will, we get some leniency on the DCP rules as long as we follow the GP, as long as we state the problem as a geometric program. And essentially what this means is that we are permitted to use monomials and polynomials where we have addition, multiplication, division, and powers. That is what is permitted above and beyond DCP when we call the GP mode. And let me just, I don't remember if I covered this in lecture. I think it'll actually come up in a future lecture. So let me talk really quickly about polynomials. The easiest way to explain this is to just pull up the wiki. So here, a polynomial is a function that has this specific form. I think the easy way to understand it is the description down here that compares a polynomial to a polynomial. So in a polynomial, the exponents have to be non-negative, but the coefficients and the independent variables can be any real numbers. For a polynomial, the exponents are arbitrary, but the independent variables and the coefficients must be positive real numbers. Polynomials come up, the only place I've ever seen them come up is in the context of geometric programming, which we will talk about in class. But just for the purposes of this discussion, that's what a polynomial is, and that's what is being permitted here when you call CVX in GP mode. Okay, so that is one example of using CVX to solve a reasonably real-world, reasonably complex problem.